Well, good evening, everyone. Thanks. There's a few seats on the sides here, so if there's people in the back that want to come up and grab some seats on the sides, feel welcome to. My name is Robert Quimby. I am the director of the Mount Laguna Observatory. I'm also a professor of astronomy at San Diego State University. And today, I'm going to tell you a little bit about what we do as astronomers, as research astronomers. Not just... There's a lot of astronomers here, but some of us do research as well. I want to tell you about the research side of astronomy. I also want to tell you what we do at the observatory, and I want to specifically talk about some of the research that I do as an astronomer at the observatory. So that's the plan we have for today. You guys having a good time so far? Enjoying? Seems like it's a good crowd out here. All right, let's just get into it then. Do you guys know about the Mount Laguna Observatory? If I say those words, does that sounds like a plausible place that's very close to here? Yeah. Is it out of focus? I feel like it's out of focus, don't you? I think I pushed all the buttons I could find, so maybe if I unpush them. Right, maybe try this. There we go.
Well, now it's fuzzy on the bottom.
Now it's fuzzy on the bottom.
That's the important part. So.
All right. Well, you get the top half, yeah. It's just my name on the bottom, so we won't worry about that. All right, so San Diego, over here, we're up here. Julian, SDSU Observatory is right here. San Diego State, or Mount Laguna Observatory is right there. More famous observatory you probably know about, Palomar, it's up here, right? But we're a little bit closer to Julian here down at San Diego State University. We can see that other observatory, Palomar, from our observatory, so, oh, maybe you can if it's in focus. There's a little white dot right here. Do you believe it? That is actually the 200-inch dome at Palomar Observatory. So we can see it from our observatory. I don't think they can see us because we don't have any glass that's that big there. They have some giant telescopes. We have some more modest-sized telescopes. This is what we have. We have an array of telescopes. We've got the Buller telescope. We've got the Claude telescope, Smith telescope. This is our workhorse here, the Your Name Here telescope. So if anybody wants to change the name of that, we can organize that. We do also have a telescope right here. It's not pictured. It's kind of hidden back here called Eriscope, and I'm going to be talking about that one in particular tonight. All right. Here is a view. This is taken with a camera we have that is basically a fisheye lens that just looks straight up at night, and that's our sky that we get from the observatory. I don't know how well that shows up in the back. Maybe is it okay? Do you see the Milky Way? Yeah. So if we're lucky tonight and this weather holds up, you might be able to see the Milky Way here as well. We do have, since this is a dark sky event, I wanted to highlight that there are some parts of the sky that aren't as dark as some other parts. These are the parts that are near San Diego, Escondido, Tijuana. So when we get close to the west here, in our view, we start losing their stars. You see they just drop out because that's where the city is. But we still, fortunately, have a good area of sky where we're not too impacted by light pollution, as we call it. So we can still see the stars, even the faint stars, and we can do some science over here. All right, so that's a quick introduction to the observatory where it is. Focus might bother me here. How are we doing with the focus? The bottom is kind of losing it. I don't know if I could do anything about that. Let's see, focus, keystone. That's not a keystone effect. I can try. Oh, what do you know? I'm not going to touch it again. That was perfect. All right.
That's the first time the whole thing's been.
All right. See, I'm a professional astronomer. I know how these things work. I want to tell you about professional astronomers. Everyone knows what an astronomer is, but actually I've learned nobody really knows what I do. When I talk to people, they have an idea. A lot of people believe they know what astronomers do. It's a pretty good idea when I say the word astronomer, what that means. My job is actually probably different than a lot of you think. You might think that I'm the guy here that looks up at the sky and says, hey, that star right there is Antares. It's in this constellation of Scorpio. Do you guys know Scorpio constellations? You probably know better than me, actually. So this is one of the few constellations that actually looks like its name. It's a scorpion. There's a tail that kind of wraps around here. Whoop, if I can see. Oh, there it is. It goes down like this, wraps around. There's the scorpion's tail. And you can see this tonight, by the way. Just look south. and this is what your view is going to, you won't see the color. The color is, you know, you need a long exposure of the camera, but you'll see the Milky Way, and you'll see Scorpio going up there. So there are people that can name stars and say, this is Antares. This is Antares, by the way. I do know that one. I grew up in a household that did do amateur astronomy. So I went to star parties when I was a kid and looked at the sky. And I learned Antares. I know that one in particular because it's a reddish star. Kind of looks like Mars. And Antares means opposes Aries. Aries being the other word for Mars. So this is kind of Mars's rival right there. It's a cool story. Do you guys know this star right here? Dashuba. I did not know that. I don't know this one or this one or this one. The only star whose name I know in this entire image is that one right there. Because I do different things. I don't name the constellations and the stars and keep track of it. I've actually never taken a course that had me memorize names of stars or constellations. What I do is I do science. So as a scientist, I ask questions, and then I try and find a way to answer them. So I ask questions like, why is this one red and that one's blue? How can I figure out what that difference is? How far away is that star? What's it made of? How hot is it? These are the kinds of questions that we try and answer. And one way to do it would be to open a book and look at that, but somebody had to figure that out. And that's my job. I have to figure out, how do I figure out how hot that star is, what it's made of, how far away it is, when I can't touch it. So kind of the definition for me of astronomers, I'm studying things that are so far away that I cannot interact with them. I can't interact with them. I can't touch them, I can't smell them, I can't taste them. I don't have a measuring stick that reaches them. So how do we figure out how far away it is, what it's made of, without getting there and touching it? All right, so that's what we do. Let me show you how. First, I'm gonna get some water. Hydration is important. Okay, there's basically one thing that I can do as an astronomer, professional astronomer, is I can collect light from these distant objects. And then I can study that light, and I can use that to figure out what these objects are. So one of the ways we do this is we take pictures of the sky. So we have digital cameras, very similar to the digital cameras we all carry around, except for these are much more expensive and much higher quality. And their job is to record basically how much light we get from each patch of sky. So we point our camera at somewhere in the sky, we take a picture, and what that's doing is it's counting photons. How many photons are we getting from that little patch of sky? And each pixel on that detector, you know, you get like a 4 megapixel camera or whatever, you get 4 million little pieces of information saying this patch of sky is this bright, this patch of sky is this bright. And we use that to figure out things like how far away are stars. I'll show you how. All right, first thing we gotta do is we gotta kind of get adjusted to the types of images that we're taking. This is an image that one of my graduate students actually took at the Mount Laguna Observatory with the Your Name Here telescope. And this will give you an idea of what we have. So first thing you have to do when you look at this is you have to get some sense of the scale. So how big is this on the sky? You know, when I point my telescope there, I get there, but I don't get over there. So what's the field of view? How big of an area on the sky can I see? So to figure this out, what you need to do is you take your thumb and you put it at arm's length and you look at your thumbnail, right? Do it, come on. Makes me feel good. See, yeah, I know, I feel like I'm doing a good job. Now look at your thumbnail, and if you take that and you divide it into 4 pieces, and you take one of those pieces and you divide that into 4 pieces, that's how big on the sky this image is.
Wow.
It's a tiny little speck on the sky. This is typically what we're doing as astronomers. We can't usually get the whole sky all the time. Now this is a very deep image. So we took a 10-minute exposure with our 1-meter telescope. This star right here, this big bright star, if that star was 10 times brighter, you might be able to see it with your naked eye. So if you actually looked at this patch of sky with your eye, you would see nothing. Just dark black, just pitch black. Okay. When people look at images like this, you see this big star and you think this is the biggest star, it's this big, right? And you think this is a smaller star, it's this big. And this one is a tiny star, it's that big. Actually, it doesn't work that way. All of these stars, all the stars you see in this image are so far away, we can't resolve them. And what I mean by that is the actual size, that angular diameter, is much, much, much smaller than even 1 pixel. You look at 1 pixel, tiny, 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 tiny fraction of that is how big that star actually appears. So what you're seeing here is just glare from that star. This is light from that star, but it's spread out because it's coming through the atmosphere and because the optics, there's different reasons it gets dispersed. So you can kind of see this, but you can change the scale, just change the contrast, and now it looks smaller, right? It's the same exact image. All I did was I just changed the way I'm showing you these numbers, right? And I can keep making this smaller and smaller, but it's much smaller than 1 pixel. All right, so here's the test now. We want to actually learn things about stars, and maybe do they have planets like we do? But we can't see those planets. They're too small. So how do we do this? All we have is the light we get from the star, and so that's all we can use. So we can, actually this is some research that's done in Mount Laguna Observatory. This is again data taken from our 1-meter telescope. And we were able to figure out that there was in fact a planet around a star. And the way you do this is you look at the star and you collect light from it, and then you wait for that planet to go in front of it, and when it goes in front of it, it blocks a little bit of light. And so that star appears just a little bit fainter. So if you're looking at the stars this bright, this bright, this bright, and then it gets a little fainter, and then the transit ends, the star crosses all the way across, and it goes up again. And so by looking at this little dip in light, we can say that star has a planet, even though we can't see the planet. You guys with me? Yeah. All right. So we can learn something about it. All right, here's another cool thing we can do just by taking pictures. This little fuzzy ball right there is actually a comet. And now, I took these images with our 1-meter telescope. I don't usually study comets, but I had a collaborator that said, we got this really cool thing, you got to take pictures of it. So I did. Its name is 2I Borisov. Borisov is the name of the person who discovered it. The 2I is the interesting thing. What can we do with these images? What we can do is we can see this object moving through space, right? And we can see what direction it's going, right? You all know it's going this way, right? So if we took later images, it'd be down here, down here. You can also say, well, it came from that way, right? So if we take images over time and we see how it moves, we can figure out its orbit. How is it orbiting the sun? Where did it come from? Where's it going? This one has an interesting story. This did not come from our solar system. The I here stands for interstellar. This is the second interstellar object ever discovered.
Wow.
And by observing where it was, we were able to figure out that it came from somewhere far, far away. It passed by the sun and it left, and it's gone. Never to return. So first of all, that's pretty cool, right?
Very cool.
Second of all, it gives us an opportunity. We can now study an object that came from another star. Is it made of the same stuff that our comets are made of? Let's find out. How do we do this? We're going to take pictures again. Just take pictures, see how bright it is. And what can that teach us? This is complicated. Sorry, I'm showing you like a real plot from a paper now. But basically, up on this plot is brighter. So as you go up, you go brighter. And as you go this way, the object, the comet is getting closer to the sun. Now, as a comet gets closer to the sun, what happens? It's got ices in it. Those ices melt or sublimate, and they make a big gas cloud around the nucleus. And that cloud reflects sunlight. And so the bigger that cloud of gas, the more we see it and the brighter it appears, right? So as that object gets closer to the sun, bigger cloud, we see a brighter comet, okay? Now, different types of ice melt at different temperatures. You're saying, what different types of ice? There's water ice. What's another type of ice? Carbon ice. Yeah, so then there's all kinds of ices. There is dry ice, carbon dioxide, frozen carbon dioxide in comets. That melts farther out in the solar system. You can be much farther from the sun and it'll melt. It'll sublimate, make a big cloud. So these observations show that when it was pretty far away from the sun, it had already formed that comet. It already had some ices melt, and it was bright. So this blue line here is saying if it just had water, it would be this bright. This is saying if it just had carbon dioxide, it would be this bright. So we say, hey, that guy had carbon dioxide in it. And then eventually, it also had water ice in it. You can see it fit the blue once it got close enough to melt. So this comet was made of water ice and carbon dioxide, and it turns out that's what comets in our solar system are made of as well. So our neighboring object here, just from another solar system, that other solar system is very similar to ours. Did we get that one? That's a little more complicated. I'm going to build it up. All right. Now, what else can we do? We can use a technique called spectroscopy. This is where we get really powerful observations. So you may know this. You take a source like the sun, you take its light, you shine it through a prism, boom, beautiful rainbow, right? What we're doing here is we're taking white light, all the colors of the rainbow are here in this, dispersing them, and then we see how much blue we got, how much green. And what we can do is we can see the relative amount of blue to red, and then we can start measuring not just the total light from the star, but how much blue light is there, how much green light is there, how much orange. And then we can start learning about the object in detail. One very important thing, like you studied your quantum mechanics before you came here, right? You ready for it?
That's right.
If you have light from a source like this, it's just putting out all the colors of the rainbow, and you shine it through a cloud of gas, that gas has atoms in it, and those atoms will absorb the light. But they won't absorb the light, just any light. They only absorb light at specific frequencies. Now, why do they do that? Because you guys might have studied this at some point. You have an atom, and remember, it has those energy states, and the ground state, n equals 1, n equals 2, like that. And you're like, why is this important, teacher? Like, it's important because each element, hydrogen, helium, carbon, oxygen, each one has a unique pattern, a unique set of energy levels. And so if we see absorption at this unique pattern, I can say that cloud of gas has hydrogen in it. So I don't have to go and taste it or smell it. I can just look at the light and look for those absorption bands and say, that's a cloud of hydrogen. If it had helium, I would see different lines in different places. So we can use spectroscopy to learn about distant objects and what they're made of. So here's another example. This was, again, data that was taken at the Mount Laguna Observatory. This is a spectrum now, so this is wavelength, and I put the rainbow here so you can see all the different colors. But when we plot it, we just plot how much light did we get at each one of these colors. So you can see over here in blue, we didn't get much light. Over here in red, we got more light. So if you looked at this object, it would look red, right? More red light than blue light means it's a red object. All right, this object has a name. It's called Betelgeuse. You guys know Betelgeuse? I'm only gonna say it twice. Don't worry. This is a red star. If you stay up late enough, maybe you'll see it tonight. It's probably it's past my bedtime, but it's a red star in Orion. Remember a few years ago, back in the before times, it did something weird. It got really faint. Like if you'd seen it a lot and you went out one day and you looked at it, you'd suddenly notice it's very different than it used to be. What happened to it? Well, at the time we didn't know, so they took some spectra of it to study it. What they do is they looked at the spectra and you got notches from hydrogen. So, it's got hydrogen, it's got some magnesium, it's got some sodium, but it also has these broad dips here. These broad dips are from a molecule called titanium oxide. That's two atoms stuck together. Molecule. Now, the thing about molecules is if you get them hot enough, they break apart. So it has to be pretty cold. Cold is, a few thousand degrees, but, cold for a star. It has to be pretty cold for them to stick together. So what this means is we can use these features to measure the temperature of the star. The more of this titanium we have, the cooler the star is. The hotter it is, the more it's going to break titanium oxide apart, and the less of this feature we see. So we can use that to measure its temperature. Now, why do we care about this? We didn't know what happened to Betelgeuse, why it got dimmer. We thought maybe one of two possibilities. We thought first, maybe it started putting out less energy. Maybe the star just cooled down. That would make it look fainter. The other possibility is that some cloud of dust just went in front of it and blocked it. So if that happened, it would be the same temperature. So what we did is looked at the temperature. I didn't do it. This is some of my colleagues did this. And they looked at this and they said, these bands are not changing, the temperature is not changing, so it's probably not changing temperature. Instead, there's probably a cloud of dust that's coming across and blocking it. And that's why we think the dimming happened. Okay. How are we doing? Good. All right. We learning anything?
Yeah.
All right. All right. I want to get into now what I do specifically. I study transients, astronomical transients. These are things that are not there, then they're there, and then they go away. That's what a transient is. So they include things like novae. These are eruptions on the surface of white dwarf stars. It includes supernovae, which are stars that actually explode. Some of them blow apart completely. Some of them leave little neutron stars behind. Some of them are caused by massive stars that blow up. Some of them are caused by little white dwarfs, which merge together and blow up. I also sometimes study gamma ray bursts. These are very exotic events where you can have a big supernova that has really strong magnetic fields and it powers its jet coming out, or it can have two neutron stars, the products of some of these supernova that merge together and make a jet. So I study these types of objects, and well, first of all, there still is the little boy, astronomer in me. So I study these because they're just cool, right? These are huge explosions in space, and that's just cool. But there is another side to this. So why are these important? I want to show you this table. You didn't know there was going to be like a science in here, did you? You thought I was just going to show pretty pictures. You didn't think the periodic table was going to appear. Periodic table, these are all the elements we have, the different atoms we have in our universe. And it started with the Big Bang. When we had the Big Bang, 13 odd billion years ago, the universe was very hot. It had a lot of exotic particles. It cooled down and formed hydrogen, protons. And then those protons, it was hot enough that they can smack into each other. You get 4 of them together and you can make a helium. And you can add a couple more and you could get lithium, a little bit of lithium. And then the universe kept expanding and it cooled down and it got to the point where you couldn't make anything heavier. Very quickly, you just had hydrogen, a little bit of helium, tiny bit of lithium, and nothing else. That was what was made after the Big Bang. Now, if you look around, you don't see much hydrogen or helium or lithium. Well, we all have lithium in our batteries now for our devices, but most of us, like the grass here, the tarp, the screen, is made of things like carbon and oxygen and iron and magnesium. These were not made in the Big Bang. Where were they made?
Exploding natural stars.
They're made in stars. They're made in stars. That's what stars do. Stars take light elements like hydrogen and they make heavier elements like helium through nuclear fusion. They smack them together in the cores. That's what our sun's doing right now. It's taking helium in its core and it's taking hydrogen in its core and it's making helium. Now, the problem with this is that all those elements basically just get locked into the center. They just sink down into the core. So you end up with, like our sun right now has a big ball of helium right at its core. And at the end of its life, it's going to take that helium and it's going to start smacking and making carbon and oxygen, and it'll make a white dwarf, which is a very compact, crazy object with basically just carbon and oxygen. Now, that gets locked up. So how do we get that here to have calcium in our bones or iron in our blood, or if you got jewelry, where did all that come from? Well, that's where the exploding stars come. If you can take that star material and blow it out into space through an explosion, then you can see the next generation of stars. So this happened. Before we existed, there had to be supernova. There were supernova that enriched our cosmos and made us. We're made of stars.
Yes, we are.
So we want to find these things and we want to study them because we want to know about us. So how do we do this? We look. But we do surveys where you look in one patch of sky and then you go back and you look at it again later and you look for things that changed. If a star blows up, it gets brighter for a little bit of time. It wasn't bright before, now it's bright. And now you know where to look and study it. This is a telescope that's up at Palomar. This is a 40-inch telescope that has been doing surveys for decades now. I used to work at Caltech and I used this telescope using a survey called PTF. And this is now the field of view on the sky. So for reference, this is the moon, and this is how big that field of view is. You might look at this and say, wow, it's a huge field of view on the sky. Do you guys know how big the moon is in terms of your thumbnail? It's about 1/4 of your thumbnail. Do it sometime. So sometime when you see the moon, go out and block it with your thumb. It'll completely hide the moon. You don't think about it. You think of the moon as being this big thing, right? It's tiny in the sky. Look at it. But we have some telescopes that have, like our telescope has a field of view which is a little smaller than the moon. There's some wide field. This is called a wide field survey. It's got an area that's bigger. There's also a newer survey that's running right now on this telescope. It's called Zwicky Transient Facility and has this large field of view. And what they do, I'll show this little movie here. So if you look on the right there, this is my all-sky camera from the Mount Laguna Observatory, but I'm going to show you what Palomar did one night. So if you look at this little green waffle that's going to appear, that's where they're looking. So this is a time lapse. You can see time ticking away here, minutes and going by pretty quick. And what they're doing is they're looking all of the sky, tiling it, trying to cover the whole sky. Now, there's a tiny little red dot here that if you got here early and in the front row, you can see. I would argue that's the most interesting place to look in the sky, and you'll notice most of the time, I just passed it a couple times, but most of the time, that's not where this telescope is looking. Most of the time, you're looking somewhere else. All right. So there you go. That's a one whole night in a minute or so, time lapse. Okay. I want to show you now what we do at the Mount Laguna Observatory. So we have also a search using this instrument. This is a little, it's a littler instrument. It has these little telephoto lenses basically in it. Each one's about that big, it's about 6 centimeters. But these have a really wide field of view. So we can cover a huge area of the sky. So I'll show you the version of that same movie, so same sky, but now I'm going to overlay images from this telescope. This is also a movie over here, and that's the sky area we cover. So you can see what we do. We got these 20 or 19. Sometimes this works and sometimes it doesn't. There's that red dot again. You can see now we're looking at it, and we're taking exposure every 2 minutes of this spot over and over and over and over and over. So if something interesting is happening, well, sometimes the camera stops working, but then it works again. Okay, that's just how technology is. And so we have these this nice coverage of that spot in the sky. So if something interesting happened during the night, we've got a whole movie that we can go back and play. Okay? So why did I show that little red dot? Because something interesting happened there, of course. We didn't discover it, Palomar didn't discover it, but a few hours after we took these images, an amateur astronomer in Japan looked up and saw a star that wasn't there before. He found a nova, right where that red dot was. So the next day, I heard about it. One of my colleagues down the hall said, "Hey, what did Everyscope do? Did we get any images last night?" Yes, we did. So I want to show you that in a second, but first let me show you what happened without Everyscope. So this is the usual way that we follow up these nova. So this is time here in days, and this again is how bright it is. This is where it was discovered. The amateur astronomer in Japan discovered it here. One of his buddies took another picture of it, then they announced it, and all kinds of people started taking pictures of it, and it faded away over time. So it was faint before, it got bright, and then it faded away. But usually we miss this part, because it's hard to find this until it gets really bright. So no one was looking there ahead of time, except Everyscope. So we got to watch it explode in real time. We caught it in the act. So this is something that was never done before. No one's ever had a brightening event like this before.
What does color mean?
What was that?
What does color?
Colors are different telescopes. So this is from our observatory, the blue and the purple there. Gray are from amateur astronomers. Green are also amateur astronomers, but in different filters.
So you collaborate with many observatories in the world?
Sometimes I do. On this one, we had pretty good data set, so I just said, well, actually, I did collaborate on a paper with some other people for this, but then we also went back and did a special analysis just with our own data. So I showed you the data, showed you getting brighter, but again, I also have the images, so I can show you the movie now. So here's the movie of a nova exploding in real time. Now you notice these are all stars, and they look kind of funky. They look like, to me, they look like Klingon bird of prey. I don't know if you guys are fans of Star Trek, but our telescope was a little bit out of focus. All right, but right there, if you didn't see it, boom, star exploded. All right, so dramatic pause to drink water.
Can you estimate the distance to this nova?
We can. There's a lot we can do with it. It's a few kiloparsecs away. Different people have different ideas about what the actual distance is. Let me show you what we can do. All right, so we're going to get sciencey again here. So this is a nova. And what a nova is, I mentioned earlier, is you have a white dwarf star. So you got a picture in center right here, a little tiny prick of light, that is a white dwarf. Now, when you look at this, you see this big star over here, and you see this little thing over here. This is actually just a big ball of hot air. It's very little mass here. All the mass is basically right here. This is the heavy part. So this star is actually orbiting around this. And this white dwarf, again, is a dying ember of a star similar to our sun. So it's the end of its life. It's taken its hydrogen, it's burned it into helium. It's took the helium and it's made carbon and oxygen. It took all that carbon and oxygen, and that was all it could do. It couldn't burn anything else, so all the carbon and oxygen formed this very, very, very incredibly dense ball called a white dwarf, and that would have been the end of it. That'll be the end of our sun. But in this case, this guy had a buddy, all right? And eventually they got close enough together that this star, which remember, it's tiny, but it has more mass. So it can, when it got close enough, this star, it started